So this video is on ionic, covalent, and metallic bonding, and I want to point out that these are considered intramolecular forces. We're actually going to end the unit with intermolecular forces, so I want to make sure you know the difference. So we're going to start with metallic bonding. So metallic bonding is bonding among metals. So what happens is we have cations. Remember, metals form cations or positive ions, and they're surrounded by our mobile valence electrons. And we call this the sea of electron theory. So notice we have these positive ions over here, and we have these electrons all around. And so that's why it's called the sea of electrons theory. So there's lots of characteristics of things that metallically bonded. That includes that something that's ductile or malleable, meaning we can bend them or put them into sheets. They're good conductors, they have high boiling points, and they tend to be strong. And metal atoms also arrange themselves in compact and orderly patterns called crystalline structures. So each metal will also have a crystal shape. So if you look on the back of your periodic table, you'll see kind of examples like this next to the elements. So you'll notice like iron has a body-centered cubic structure. We have an atom in the middle, and then each corner has an atom. If you'll notice the face-centered cubic structure of like aluminum, you have an atom on the outside plus the corners. Here's like titanium and zinc. They have hexagonal, and there's other structures as well. If you go into the engineering world, you'll probably take a class like material science, and you would hit this stuff a little bit harder. Also, in this particular Google slideshow, I want to point out that all of these headers are hyperlinked videos, so you may want to look at those to get a little bit more information on these different topics. So alloys is a mixture of elements where at least one is a metal. So it's like a metal solution. And we make these by melting a mixture of metals and letting them cool. And usually we're trying to come up with whatever properties we want, and we could look at certain kind of phase diagrams to decide those properties. So maybe we want to add two metals together for strength. Maybe we want it to be able to be flexible, all different things. And so there's different kinds of alloys. There's a substitutional, there's an interstitial, or a mix of the two compared to a pure metal. And so these are just different kinds of atoms. So notice this is a smaller one with bigger ones and things like that. So examples of alloys, one is sterling silver. So if you think about silver jewelry, copper's been added to it to make it a little bit harder because pure silver is super, super soft. Bronze is a mixture of copper and tin. It's used kind of like for looks, like for art. Cast iron is used in cooking. So it's a mixture of iron and carbon. And if you can think about for cooking, why that would be useful and how you can throw it into the oven. Stainless steel is a mixture of iron, chromium, copper, and nickel. And so you want that to be super strong. Now surgical steel, notice it's a very similar mixture as above, but now we've added molybdenum. And so again, that helps us to have really sharp instruments and make things sterile. Now, ionically bonded things, we're going to do a lot with that in this class. Notice again this hyperlink as well. It is a bond between a metal and a nonmetal, or a metal and a polyatomic ion sheet, or polyatomic ion. Now, polyatomic ion is a gang of elements that work together, and then you'll get a sheet about this later. So an ionic bond is formed by an electrostatic attraction between a cation and an anion. So basically you have a positive ion with a negative ion, they get attracted and they transfer their electrons to help satisfy each atom's octets. So if your compound starts with a metal like these guys, it is ionically bonded. Properties of ionic bonds include that they tend to be hard, they're solid, they're inflammable, they tend to have high melting or boiling points. They're also often soluble in water, and they have defined crystals. Notice it's kind of like those crystalline shapes we saw on the back of the periodic table. And they have high electronegativity differences between elements. So if you think about that, here's the periodic table. If I have a metal over here bonded to a nonmetal over here, and we know electronegativity increases in this direction, that is a very big difference between those two values. So here I have some Bohr diagrams to tie things together from the previous unit. So notice sodium has that one valence electron on the outside, and over here chlorine only has 7 electrons. So what happens is this guy is going to go over here to make chlorine feel 8, and when that happens, it gives a -1 charge for chlorine. And then over here on the left, we have sodium without that outermost electron. And so then here we go. They have now been attracted because of that switcheroo, and now we have sodium chloride. Now covalent bonding is going to be a little bit different. It's covalent bonds are between nonmetals only. So if your compound starts with a nonmetal, then it has to be covalently bonded. You might also see these called molecular compounds or molecules. So this electrons are shared between atoms to satisfy the atom's octet. Covalent bonds can be either single, where they share 2 electrons. They could be double, where they share 4 electrons, or triple, as they share 6 electrons. So the bigger the bond, like nitrogen here, a triple bond, is going to be stronger and shorter, whereas a single bond is going to be longer and weaker. Examples of these could include water. C2H5OH is an alcohol, and HC2H3O2 is vinegar. Properties include that they're often gases, flammable, they can be soft and squishy, brittle, they can have low melting and boiling points. And then they would have low electronegativity difference between elements, because if you're looking at an element over here and one over here, they're very close together in that electronegativity world. So covalently bonded things, they don't necessarily share electrons equally. There's kind of a tug of war that happens, and it's because of that electronegativity difference. So when they don't share evenly, we use the term polar, or something has a dipole. So if I look at hydrogen and I look at fluorine, and these two could be bonded, we know fluorine is a very, very electronegative element. And so what happens is electrons get tugged towards fluorine, and so fluorine's going to be kind of an electron hog, making it have a partial negative charge, leaving hydrogen with a partial positive charge. So fluorine feels more of the electrons and hydrogen doesn't. And when this happens, that means that thing has a dipole. We could actually calculate it, and that's called a dipole moment. Or for now, we're going to say that is a polar covalent bond, or this has polarity. Okay, so the minute you have 2 different electronegativity values, it's going to be polar. Now we do have our diatomic molecules. They are nonpolar covalent molecules because they can share perfectly evenly. There's no tug because they're the same element. Now there's a phrase I want you to commit. I would make sure you have this on your help sheet, that symmetrical molecules are nonpolar and asymmetrical molecules are polar. Now also, if an element has a lone pair, that's going to add to the asymmetry. And the reason this is important is if I look at a molecule like this one, I could put bond arrows between the C and H, and those bond arrows would cancel out. And I could do the same over here, and they cancel out. If our bond arrows all cancel out, it's going to be nonpolar. However, if I have C and H and a C and H, and let's say there's a fluorine, my C and H bond arrows on the left and right can cancel. But then notice when I draw it to fluorine, the bond arrows all go in the upwards direction. So that would make this molecule polar. So what's going to happen is we have these individual bonds where we can see some polarity, but these bond arrows can ultimately cancel out, changing the polarity of the molecule. So here this is polar because it's 2 different compounds. This one is polar because it's asymmetrical and also has a lone pair of electrons, and these bond arrows do not cancel out. Now BF3, these bond arrows in 3 different opposite directions, it's symmetrical, makes it nonpolar. Here we have carbon tetrachloride. Notice the bond arrows are all in opposite directions, making it nonpolar, but the minute we change one, if they're the same, it becomes polar. And so there's a little segment we're going to add to the fruit snack notes where we're looking at that symmetry. This is also a picture that I think helps with understanding the polarity. So notice on the left side is nonpolar molecules, and on the right is polar. And the big difference with the polar molecules is notice one of these gets a little bit different. They've just changed a couple of these atoms, and so it changes that symmetry. So hopefully this helps you understand the basics of our bonding.